So I think it's time to start. It's my pleasure to introduce to you Manish, Kumar from KU Leuven, and he's going to talk today about quantum dynamical semigroups and derivations on von Neumann algebras. The floor is yours.
Thank you. And thank you to the organizers for giving me time to speak here. So I will talk about certain theory in von Neumann algebras, which somewhat relates to what Jacopo was also talking. So what Jacopo told was this history of how you can prove certain von Neumann algebras are prime or not. So let gamma be a discrete non-animal ICC group. Then he showed that L gamma is prime if gamma is biexact. So prime means that this is not isomorphic to tensor product of two one factors. And so Ojava is the one who really started this kind of results, where so before Ojava it was known for free groups, but what Ojava proved was for a very large class that he called biexact. And then he actually proved a stronger result, that this is solid for this is. So I will just recall the definition. So if it's diffuse, then its relative commutant is injective. And this implies this when gamma is not evident. Okay. And then I think some 3-4 years later, Jesse Peterson came up with another approach to prove primeness and even solidity, where he gave some example of group von Neumann algebra which are solid, and I am not sure if they are biexact or not, but I will tell you what those groups are. Okay, so that is where derivation theory comes into the picture. So one of the approach that Ojava and Popper took in his strong solidity result was something called deformation irrigidity. So what deformations are essentially? So let me just describe that. So the definition I am going to write it for general setting, but many of the results will be in the tertiary setting. So M is a von Neumann algebra, phi a normal. Is this visible? State. So a quantum dynamical semigroup. So unlike many other talks where you had group action, this is not actually a group action but rather a semigroup action. So QMS on M equipped with this state is a semigroup of completely positive maps. So these are completely positive maps on M, indexed by non-negative integers, non-negative real numbers of normal QCP maps, and it satisfies the semigroup property. So you start with identity and then you can build up some group like this. And because we are in a fundamental algebra setting, we want some kind of continuity with respect to weak topology. So we want this is continuous, where on M you take weak star topology. And we also assume, which is in literature, many places you may not see this, but we also assume that all of these UCP maps are state preserving with respect to the state that we started with. Okay? And for this talk, I will have another assumption. So a QMS is called GNS symmetric. If you can, so this theta, this property actually can be used to extend this theta from M to the GNS space of L to M. So maybe let me just write that first. So since this implies that there exists theta, this is just a notation, 2 is the L2 extension on the Hilbert space that is coming from the state phi, and this is a contractive map, satisfying this theta 2 when you apply it on the cyclic x. So this is the cyclic vector, so maybe I will write just here that this is just the notation. So I am integrating the second variable, and this is just a notation for the cyclic vector induced from there. So it satisfies this. Okay. So once you have this, then what GNS symmetry is telling. So definition, theta t, this QMS is called GNS symmetric. If these maps are actually self-adjoint. So if you take this, so this is inner product with respect to phi. So what this actually means is that phi of theta x star y is phi of x star theta y. So we will have this extra assumption, and there are other symmetry that one also considers, like for example KMS symmetry. When you, instead of taking the GNS inner product, you take KMS inner product, and you want your map to be self-adjoint with respect to KMS inner product. So when you are dealing with a non-terrestrial state, then there are various ways to embed M into the Hilbert space, and then you have a lot of ways to consider the symmetry there. Okay, so one example. So let's take the group von Neumann algebra. So discrete countable group. And on group von Neumann algebra, essentially you can give examples of this coming from co-cycles of representations. So what they are? So let be an orthogonal representation. So here H is a real Hilbert space and pi is a representation, and B is a cocycle. With respect to phi. And then given this cocycle, you can generate these positive definite functions. So here this notation, let's say this. Maybe I should do GH. Okay.
So big G is gamma, right?
G is in gamma. Yes. G is in gamma and P is.
You have a capital G there.
Oh yes. Sorry. Yeah. And then once you have a positive definite function, then you can get completely positive map on the level of group for Neumann algebra. And how you can just define. On the generating unitaries, you can just define like this. And then the way we had started with a positive definite function, you can show that this is actually a trace preserving completely positive map, and it gives you a semigroup. Because they also, in some sense, form a semigroup. Okay. So this is J symmetry with respect to the canonical trace on the group phenomenon. Okay. So let me give you a definition of how you can try to think cocycles on general phenomenon algebra, and that is where the definition of derivation comes into the picture. So here, for a moment, I am taking M to be a tracial phenomenon algebra.
So, sorry, can I interrupt?
Yeah.
So, how rare is this, the existence of this cocycle?
How?
Which cocycle?
In the example,
Yeah.
you take an orthogonal rep, right?
Yes.
Is it something you always have?
This is like assumption. Like, let's have this, and then you can form.
Yeah. For which groups do you have, or is it something that you always have?
Well,
Like
we have
Essen groups, you don't have any interesting cocycles. Otherwise, you always have.
Sorry?
If you have a Custom group, you don't have interesting cocycles. I mean, that's or are trivial somehow.
Okay. So it's low rank property, the existence of T.
Yes. So
Okay. Okay.
Yes, for property T, yes. Like,
Okay.
one cohomology is like trivial. So. Yeah, so like that is where we will discuss some weaker notion of property T. And for them, we will see some. And H is a Hilbert bimodal. So what does it mean that H is a Hilbert space and you have a left and right action of M? an algebra representation. And normal representation phi from M to BH. So this gives you the left action, and you have the right action, which means that you have a representation from the opposite fundamental, and they commute. Commuting representation. Okay, so once you have this, then a derivation can be defined like a derivation is a closed, well, this definition, this closedness is usually, I should take it, so is a densely defined closable unbounded operator from, so this is subset of L2. So it's a densely defined unbounded operator from L2 to H, and it satisfies some kind of co-cycle property like this. So in this sense, what it will mean is that delta xy so you can define this kind of derivative property whenever you have a bimodal and acting action of an algebra there. But here, because we are in a fundamental algebra setting, we really want to look at some specific kind of derivation. And why so? I will tell you a result by Socket and some other people, Davis and Lindsay, which says that once you have a derivation, then you get a GNS symmetric quantum Markov semigroup, and you can go back as well. So that is why we are studying here. And okay, maybe I should write it here. And you also want your derivation to be symmetric in some sense. So what would symmetric mean there is that delta is called symmetric. Because if you don't take symmetric derivation, then the GNS symmetry will not be preserved. So what symmetric means there is that there is an involution on H. So just like L2M, here it has a natural involution. So on L2M, you have this map, these operators which sends vectors like this, and this is actually an isometry, but it's antilinear, and you want delta to preserve J, which means that you should also have some kind of involution on H, and that will make sure that symmetry is also preserved. So delta is called symmetric if there exists an involution. Well, I should say that, okay, involution, so let G be an involution. What does it mean? That it's a unitary which is antilinear and its square is 1. Then delta is symmetric with respect to this if it preserves this structure. Okay. So I should also mention here that such that domain of delta is contained in M. So this is a crucial assumption. Or as well, you think M sitting inside L2M. Okay, and once you have such symmetric derivation, then what you can do, so given a symmetric derivation delta, so this just means it's densely defined, it's not defined on all of L2. You can take its adjoint, and delta is closable, so you can close it, and this really gives you an unbounded operator at the level of L2. Okay, and which means that you can do some functional calculus here. So you can take its exponential and you can define theta to be this, and this actually, well, let me just say that you define Tt. So this is a bounded operator on L2M. Okay, but there is this theory by various people which says that when you restrict Tt to M, it actually maps to M itself. So what? And there exists a QMS theta t, QMS in this sense on M, such that Tt is actually equal to this map, where this is defined here. Okay, so you can go back and forth as well. So if you start from this way, if you start from a QMS here, then you can get a derivation like this. You can explicitly construct what H there is, and you can define derivation explicitly, and then you can say that each theta t actually comes via these derivations. Okay, and at the level of groups, these derivations are actually nothing but connected to this cocycle. So maybe I should say it here.
For a symmetric derivation, is the QMS also symmetric?
Sorry?
If your derivation delta is symmetric, then the QMS is
Yes.
also.
Yes. So this is if and only if. So delta is symmetric in this sense, if and only if this is symmetric in the way we had defined. Okay, and converse is also true. I'm not stating it, but from theta t you can get it back. And in this example, if you have B, maybe let's say this is K. Just to, or maybe make it more precise, let's say this is real Hilbert space with respect to some representation. Let's say you have a cocycle, and then you can build a derivation. So what you do, you take L2 gamma, you consider its tensor with this, I mean it doesn't matter, but let's say, so this gives you a complex Hilbert space. Okay, so that is where our derivation is going to lie, and then H is L gamma bimodal. So how do you define the bimodular structure? So the left action on H is given by so you act diagonally by the representation that you started with and the left regular representation on L2, and the right action is given by, so it acts trivially here. This is the right regular representation. Okay, so in this way you can prove that H is a bimodal, and then you define delta. So let's say its domain is the domain of delta is this, and you define just this. And the way we had started from a real Hilbert space and everything, this actually is a symmetric derivation. Okay, and the QMS that we get actually, this theta t is nothing but that one. And you can go back as well, is what. So you can actually get one cocycle if you have a QMS on the group phonemic algebra, and you can use this converse result here. Okay. So there are various ways to build derivations. So if you start with one derivation on tensor products, you can build derivations. On free products, you can build derivation. But the kind of derivation that we are interested in is when this H is either the coarse bimodal, in a sense that this H is is L2 space. So this is the left regular representation. It is the case when we are interested in, and or when it is weakly contained in the left regular representation. Okay, so remember that a group has property T if any positive semi-definite function which converges pointwise actually converges uniformly. And in the sense of in the case of tracial phonemic algebra, this definition is saying that any quantum dynamical system, it converges pointwise, and property T is equivalent to saying that it converges on the unit ball. So this is definition of property T. M has property T. So this is tracial. If given any QMS, well, not QMS, but if given any net, let's say theta I of normally signals, such that theta I converges pointwise, we have that it converges uniformly. This norm is in the L2 norm. Okay. So property T that was defined by, I think, Jones and Combs translates to one Neumann algebra setting is like this. They also defined it using some kind of Feld topology. But what
I
if
think
we...
it was Kohn first.
Yes, I think so, yeah. Yeah, I think Jones and Kohn wrote another paper where they...
Later, yeah.
Yeah. Okay, so what if we take theta I to be just semigroup? What if we restrict only to the class of QMS? In that case, if you write this definition just for QMS, this converges uniformly. I am not completely sure if it is equivalent to property T, but what we are going to do is going to restrict this class to even a smaller class, and then we will call it L2 rigid. So that's what Jesse Peterson defined.
Excuse me.
Yes.
So the assumption is that you have this net of normal UCP maps, such that for every x that converts
Yeah. Yes. It
normal.
Pointwise convergence in weak star.
Normal.
In weak star topology.
Sorry?
Weak star.
Weak star. Okay, thanks.
Yes. Yeah. Here everything is weak star.
Okay.
I mean, so, or I think we can say that even SOT is okay.
I see. Yes.
This is for all x. Implies it converges uniformly on the before. So trivial for Neumann algebra is L2 rigid. So property T is kind of a rigidity property in a sense that pointwise convergence is enough to say uniform convergence. And what L2 rigid is that if whenever delta is a derivation where H is, let's say, weakly content. So I have not defined weakly content here, but if you know the weak containment of representations on groups, then this is somewhat the same, that you can approximate the coefficients here by coefficients in H. So if you are not comfortable with this, where H is, let's say, infinite direction of the course bimodal. If delta is this, then if you take this semigroup, it converges uniformly. So this convergence is always there pointwise. I mean, this is okay. And here we are actually taking infinite like operator now. This converges to 0. So this is actually a weaker condition than property T, of course. Property T asks for any normal UCP map, which is trace preserving, to converge uniformly. But here we are asking for a smaller class, which also gives us some flexibility in a sense that it is not so rigid, and we can still get some results. So what kind of results that Peterson could prove? Let me just some of them.
So reading in this way, you start assume to be defined on the whole L2.
No. So when I write this, it's densely defined.
Domain,
Yeah, so-
Densely defined.
Yeah, but this is densely defined.
It's never.
It's never bounded. Otherwise,
No,
this,
it's never
this
really
uniform
bounded.
convergence is automatic. In fact, the uniform convergence for bounded delta is automatic. Like it's inner.
Yeah.
Derivations.
It's too strong. I mean, it's fine. But you don't want to give an example of group which for which error?
Yes.
Oh, you're
Yes,
good.
I'm coming to the some
Okay.
of the results
Sorry.
that Jesse proved. So here is a theorem. So gamma is non-amenable ICC if L gamma is not L2 rigid in this sense. So what this actually means, I will just give you another way of explaining this. So if it is not L2 rigid, then you can show that L gamma is prime. So let me just mention it here. L gamma is not L2 rigid if and only if. So remember, I at some point told that all derivations on group von Neumann actually comes from cocycle. So if it is not L2 rigid, it means that whenever so this is same as saying that one cohomology. I will explain this. This is trivial. This is non-trivial. So okay, what I mean that there is a cocycle. There is a one cocycle B here. So in the left regular representation, there is a cocycle which is not here. So which is not a co-boundary. So by co-boundary I mean
Maybe it's not equivalent because the non-vanishing of H1 is equal to say gamma has a
positive
positive argument
L2 beta.
number.
But for finitely generated groups. I think for
No. For any.
for non-finitely generated group, one direction is true. I'm not sure.
This direction is true. The backward implication is true. For the third line, you're right.
Yes. Yeah, I think yeah. So this is positive implies this.
Yeah, you plus L gamma is. This is equivalent.
This is definitely.
For finitely generated group, they are
This is
equivalent.
equivalent. Yeah.
This is
Yes. So gamma finitely generated.
This is not linear.
Yeah.
I think at least what I have seen in the literature, it was written
Finitely generated.
for non-finitely generated. One equivalence was proved by Gabario, but I am not sure about the other. At least in one or two literature, I have seen this. But yeah, they are equivalent. We can stick with if we are not sure. Then we can stick with finitely generated. Okay, so I am not going to explain these things because I also don't know.
Yeah, but why the first equivalence course in the third line you wrote?
Yeah, this one.
Yeah. I don't think it's an equivalence.
So maybe there is a condition on gamma. Gamma is non-amenable and I think it's it's true for non-eliminable groups. So, okay. So, one way should be okay. So, this way is okay, right? And this is just by definition. That if it is not L2 rigid, then there exists a derivation such that this uniform conversion does not happen. And in that case, the co-cycle will not be bonded. I mean, or inner.
I mean, I'm pretty sure L2 rigidity is not fully characterized by using a property of the groups, because there one program on pop up asking to characterize which group has the Bernoulli's cocycle superrigidity. But his conjecture answer is it has this Bernoulli cocycle superrigidity only if the group has vanishing L2 Beatty number. And it is known that if gamma is L gamma is L2 rigid, then this is true. But the question is still for the open.
Okay, so maybe just let me write just one implication. So this is what is proved in Jesse's paper.
Yeah.
The other direction. Yeah, I am not sure about the other direction. Okay. Okay. Anyway, so once you have this, then it is not L2 rigid, and then it is prime. So it gives you an example of a group phonemic algebra, probably which is not biexact. I am not sure, but the group phonemic algebra is prime. Okay, and let me also write another result from the same paper.
But there is not known example of what? Of these evenience that you
So
see.
examples are like many groups. I mean,
No, groups that are not biexact but the phonemic algebra is prime.
yeah, I am not sure.
Yeah, no.
Do you have?
Ah, you're right. You're right. Yeah.
Also
yeah.
some
You're right. Yes.
Thomson groups also.
Also SH with Z1 over. Yeah, you're right.
Okay, and let me state one more theorem. This is also Peterson. So gamma is again ICC non-eliminable group. So let B be a proper cocycle. Apart from free groups, I also don't know many examples here as well. So proper Hall cocycle. So what it means is that one way to formulate is that all the positive semi-definite functions that we get, they are compact in some sense. So they are C0 functions. So one way to say is that the set is the collection of all elements for which this is bounded. This is finite. Proper means this. So this implies in particular that the group has Hager property, but yeah, here we are demanding a cocycle only with respect to left regular representation. So examples are like free groups. In this case, L gamma is solid. Again, I don't know any example when this is not biexact, and it admits such cocycle. But this is definitely not the same approach that Ojawa took, to prove solidity. And in the paper by Peterson, I also don't think he gives an example of but yeah, I will have to check more closely. And the proof is also quite different for solidity. Okay, so
So he assumes that gamma is the same as the theorem or not? Gamma is ICC?
yeah, gamma is ICC and non-amenable. Yeah. Well, if gamma is amenable, then it's automatically solid. But
Okay,
yeah.
that's
I don't think I have time to give you an idea of proof, but let me just say now what I had been trying to do in this regard. So this result is not just true for group fundamental algebra, but also true in general, where instead of a co-cycle, if you have a derivation taking values in the course bimodal and such that the resolvent is compact, then you can say that it is solid. Okay. So theorem, the proof is like the same. So delta is derivation, symmetric derivation. Again, this means that it's an unbounded operator, such that these are compact. This is a real number. Then, if M admits such derivation, so here, actually you can replace this by any Hilbert bimodal which is weakly contained there, but I am stating it just for this. Then M is solid. Okay, so what I had been trying to understand recently, which is also quite new subject for me as well. So what I had been trying is how one can try to extend this definition and these results in non-trivial settings. So now let's say M of fundamental algebra, and let's say M does not admit any trace. Okay. Non-trivial, so any normal. Most of the things that I would describe also works when phi is a weight, semi-finite weight, but let's take the state. So the initial question itself that one may ask is how to define derivations in that sense. So remember, for trivial case, delta. So for the trivial case, delta was a map which satisfies this condition. So what here I mean, so del domain of delta is contained in M, it is contained in M2 of M. So with the natural inclusion here, derivation satisfies this property. Now in non-trivial case, what inclusion here you want to take? That's the bigger issue. Like, so there are various ways to embed here. For example, X can be embedded like this. So this is the cyclic vector corresponding to phi. X can also be embedded Okay. So I am not going to describe here what J is, but this J this time is different than what you had seen in the trade cell case. Okay. There are also ways to embed. So S here is the map J that we had seen in the trade cell case. So this is an unbounded operator which sends this, and you can take its polar decomposition, and this J is the same as this J. There are various ways to embed, and whatever embedding you take and you try to define derivation like this, getting back and forth is an issue. So you don't have a general result where like what I described, like Swagit, where starting from a QMS, you get a derivation, and then starting from a derivation you can get a QMS. So in general, if you define derivation like this and take their square root, this is in general not a quantum Markov semiroot. So what one then do is, okay, so there is this recent result by Melchior Wirth that this H that you consider should also have the same kind of property that L2M have, in a sense that L2M has the operators S, J and delta that corresponds to Tomita-Takisaki theory. Then H that we are getting here should also have those kind of maps, and it also satisfies some kind of Tomita-Takisaki theory. And that is where you need to modify H there. So that is where he calls Tomita bimodal. So this comes with here, right? There is also a one parameter group of automorphism here. So a Tomita bimodal is a Hilbert bimodal H over M, which also comes with a one parameter group of unitaries and map J, which satisfies the same kind of condition that this J and this sigma is supposed to satisfy at the level of L2. Okay. And the derivation then one defines. I am not going to describe very much in detail, but what I am going to say here is that a derivation should have the property here. So this domain, again you demand it to be inside M, and it is densely defined, and it should preserve this J where this J is this. It should preserve UT, which is this, and that UT is there. So this actually induces a unitary at the level of a smaller class of M that we call Tomita algebra. So this domain actually contains like analytic group. So I am not going to say many things there, but it should preserve this. So what this UT here is, this is just okay, UT is just delta IT. So this UT is supposed to play the role of this, and it should then preserve this map. And once you have such delta, and then it satisfies the derivation condition. But the derivation condition that it satisfies is a bit different, because the right action here, in trade cell case, the right action is actually quite nice. But in non-trivial case, the right action comes via this map J, and that should also be reflected in the definition. That's the idea. Okay, so satisfying this property, you have now the notion of derivation, and then you can consider their square, which behaves like cocycle. So for non-discrete locally compact group, you can say that derivations actually comes via these cocycles. And if you consider this, then it gives you a quantum dynamicus semigroup in the definition that I have mentioned in the beginning. And you can then go back as well. Like if you start with the quantum dynamicus semigroup, you can build a Tomita bimodule like this, and it comes via this. And now, once you have this, then you can make the definition of L2 rigidity in the same way. But again, the main issue here is that if you try to define uniform convergence on the whole unit ball, it's again very strong. Just like in property T, if you have a non-unimodular group, then it cannot have property T. So the same way in non-trivial case, those kind of issues start happening. So instead of defining it on the whole unit ball, you want to say that, so here is the definition. So this we had proposed. So this is an ongoing work with that group. So M is L2 rigid if delta is a derivation like this, satisfying these, where H is a bimodular with these two extra conditions. And well, you can take H to weakly contained in the course, but H is weakly contained. Then we want this supremum. So here X is not, so X is in the unit ball, and it's also in the, Jx is also in the unit ball. So on this smaller set, it converges uniformly. Okay, so this is not so for trivial case this actually gives you back the original definition, but in non-trivial case, if you don't take this, you just take H in the unit ball, then it's a very strong definition and it does not give you many examples. So with these kind of definitions, we can actually prove these kind of results here as well. That if you have derivation taking values in the coarse bimodule with compact resolvent, then you can get your von Neumann algebra to be solid. Okay, and actually, if you assume moreover that if your von Neumann algebra has some kind of weak amenability, like in compact metric approximation property, then you can get a stronger result like a strong solidity and absence of that answer in particular. So, yeah. And we are then now trying to prove various other results. For example, we can also say some kind of fact, something like if you have a cocycle which is not inner, then you can say some kind of primeness result in this setting as well. So various results of Peterson can be then generalized to this non-trivial setting, and we are still looking for many other applications that we can get. So with that I will stop here.
examples to apply this algebra.
So, for example, so if you are familiar with free hierarchy roots for Neumann algebra, so when you take finite dimensional case, where UT is non-trivial, so you have a representation, orthogonal representation of reals on finite dimensional Hilbert, real Hilbert space, and then you can build a non-trivial for Neumann algebra. This is what Selyakhenko called free hierarchy roots for Neumann algebra. You can actually show that the derivations are so the derivations coming from Voiculescu's free what he calls it. So I don't remember the name, but you have algebra generated by linearly independent vectors, and then on each vector you define. So let's say if you have so this is a particular case of this. So if you have a subalgebra generated by some variables, well, M is the phenomenon algebra generated by this, and if you take the subalgebra like this, and let's say these operators have nice properties like say analytic and things like that, you can define these derivations which acts on the generators like this. So this is what Voiculescu considered for free groups and various other free product case. And using this, he actually proved some kind of absence of Cartan subalgebra and things like that. So if you consider these kind of derivations, in this particular case, at least, you have this setup, and you can prove that it is. But this fact was already known, I would say, that it is solid. But just to give you an example in this setting. But definitely we have more examples even from locally compact group, which is not discrete.
Other questions?
So, analog to the fact that L gamma is L2 rigid implies L H1 group equals 0. So when you talk about L2 rigid M, it implies H1 of M with which module equals 0?
Yes. Yeah. You mean this is 0. Yeah, so I think converse is not true for every group, but at least it's not there in Jesse's paper.
I have, please.
Yeah. No, I mean, is it reasonable to ask about cross-product algebra by an action? I don't know. I mean, is there 3Z acting on some projective space or something like that? I mean, where you have type 3 action, the type 3 for Neumann algebras.
So far we have not yet looked into that. So that is one place where we want to find more examples from.
Sorry?
That is
one place where you can.
Yeah.
So you didn't look at.
So far we have, but we definitely have some natural examples from equivalence relations in general.
Yeah.
But so far, do we have like those? That derivation satisfy some kind of compactness argument, so we can prove solidity? That we so far don't know, because in general it is not so easy to verify this condition. But yeah, just getting example, for sure.
Do you have an example where your theorem applies to some factors coming from quantum groups?
Not that.
Quantum permutation?
No, so the natural derivations, they actually don't satisfy this condition. But if we can find some different derivations on those quantum groups, I am not sure. But yeah, and so far again, we don't have examples from quantum groups.
Even if you know that it might be solid.
Yes, even if we, in fact, some of the examples like free orthogonal quantum group. I don't think so far we know any derivations satisfying this condition, but we know that some kind of rigidity, solidity, and strong solidity result from past.
Thanks. All right, so I think we can conclude for today. Let's thank Dan